so we did the semantics of propositional logic, and so this is what, basically the whole idea is to look at so one way of looking at propositional logic is as an algebraic system, and in fact one of the reasons for adding this bottom and top is to sort of bring in a one-to-one correspondence between the signatures of propositional logic and the Boolean algebra, right. So you have an exact correspondence between the operators, they sort of have the same signature or similar signature, right. Okay. So that is, so that was also the reason for defining this operator less than or equal to dot and equal to dot, yeah. Then we looked at these basic concepts. There is one, the concept of a tautology or a logically valid formula. When we say formula, of course I mean a well formed formula according to the syntax, the abstract syntax trees and so on and so forth. And contradiction, and there is a notion of satisfiability and falsifiability also. So we would call in terms of logical concepts, the most important logical concept that we will look at is the notion of logical consequence. Yeah, so we would say that, so supposing there is a set of formulas gamma and another formula phi, we say that phi is a consequence of gamma and denoted by this symbol. Notice that the symbol is black in color, right. So it is a metalogical concept, it is not part of the logical language. Of course I can make mistakes with color, but normally if I have not made a mistake, then this black means that it is not part of the language, the object language under discussion. And essentially we say that phi is a logical consequence of gamma, where gamma is a collection of formulas. This collection, P naught of course is an infinite collection of formulas, right. We started with an infinite collection of variables and built up the language, and that language would also be infinite, will have an infinite number of well formed formulas, right. If the set of variables or the set of propositional atoms is countable, is countably infinite, then P naught would also be countably infinite. Yeah, I guess everybody is clear about those things. So P naught, even though it is constructed from an infinite set, and it's not uncountable. Okay, so it is so this gamma could potentially be an infinite set, could be a countably infinite subset of P naught, and we would say that phi is a logical consequence of gamma if any truth assignment that simultaneously satisfies all the formulas of gamma. Yeah, so under that, so you take a truth assignment tau in which every formula in gamma is true, then phi is also true. So that truth assignment also satisfies phi, right. Then we would say that phi is a logical consequence of gamma. Remember that we are talking about propositional logic, which is essentially meant to deal with reasoning, and in general remember this in the background of the fact that I said all of logic is essentially symbolic in nature, okay. So which means that, and the notion of meaning that we have given is restricted to essentially declarative statements, okay, and it is restricted to the truth values of declarative statements under certain truth assignments. So in any logical argument, it is not necessary that the individual sentences of gamma or of phi need to be somehow meaning related in natural language, okay, because meaning for us is restricted to. So you can take completely unrelated sentences, form a collection, and take a completely unrelated sort of sentence, form phi, and if it so happens that for all truth assignments in which every formula in gamma is true, phi is also guaranteed to be true, then phi is said to be a logical consequence. So, I am emphasizing logical consequence because it is not semantic consequence. If it were semantic consequence, then we would actually assign a meaning which is much finer than just whether it is true or false, right, in which case semantic consequence may not hold, but logical consequence would hold, right. So, we are talking about logical consequence only. So, in general the sentences of gamma need not be related to each other. They can be completely arbitrary sentences like the sky is green and I am present in room number 301 today and so on and so forth, and some other sentence might form phi, and if it so happens that for all truth values, truth assignments, all these sentences are true, then we would say that one is a logical consequence of the other two. Yeah. Okay. When gamma is empty, then logical consequence reduces to logical validity, right. So, essentially that reduces to a notion of to something like absolute truth, right. By the way, so that top symbol that we use for absolute truth is a trivial example of a tautology or a logically valid formula, and that is absolute truth, right. Okay. So, and of course, as far as notation is concerned, so logical validity, there are certain things. The notion of tautology and contradiction is only used in propositional logic, it is not used in other logics, but validity is a concept that is used in all logics, right. Logical consequence is used in all logics, right. We will see that we will see the difference when we come to first order logic, but till then as far as propositional logic is concerned, validity and tautology are the same. Yeah, something being logically valid and something being a tautology are really the same. And of course, if you strike the symbol, logical consequence symbol, that is like negating it, and it is a meta negation, right. So, it is not the same as the propositional operator not, it is in the meta language that we are saying. We are essentially saying that phi is not a logical consequence of gamma, and that holds if and only if it is possible to find a truth assignment in which every formula of gamma is true, but phi is false, right. I mean that's the extent of in which we will talk about something not being a logical consequence, or when gamma is empty, of course, we are saying that something is not valid, not logically valid, or it is logically invalid, which essentially means that there is a truth assignment which will falsify this phi. So, if phi is falsifiable, then that means that there is a truth assignment in which phi can be false, and therefore, phi is not logically valid, and it is not a tautology. Yeah. Okay. Right. So, this is the first theorem. Such theorems are usually not put up in any logic book. So, therefore, what we will do is I will give a proof of this theorem which shows exactly how it has to be done, and all other following theorems which are of a semantical nature, I will just leave it as an exercise for you to do at home, right. Okay, so let us look at this, something that is actually fairly obvious, and the whole purpose of proving this theorem is to establish how from the semantics one can derive certain meta truths about let us say the meta concepts that we are defining, right, about some of the logical concepts. So, let gamma be a finite set. Yeah. If gamma is a finite set of propositions and let psi be any proposition, then psi is a logical consequence of gamma if and only if this formula, which essentially is obtained by taking a conjunction of all the formulas in gamma, arrow psi is a tautology. Okay. It is important to look at every aspect of this theorem. Firstly, this theorem really holds and is well formulated only if gamma is finite. Okay. As opposed to the normal notion of logical consequence, where gamma could be infinite, this theorem actually is a restriction of the assumption. Basically, the restriction comes from the fact that you have to form this formula. Okay. All formulas are finite string objects. So, if gamma were an infinite set, then I would not be able to form a well formed formula in the language of propositional logic. Is that clear? So, this theorem, because of this restriction, because I want to form a single formula out of the entire set gamma and the formula psi, a single formula has to be of only finite length or finite depth, and therefore there cannot be infinite, right. So, this is in some sense a restriction on, there is a question of, so what it means is supposing psi is a logical consequence of only an infinite set and there is no finite set of which it is a logical consequence, then what happens? I mean, that is a question that you have to ask, for which we will not give any easy answers now, we will postpone the answer later. But for the moment, to establish our notation and so on and so forth, let us prove this theorem. Yeah. Right. So, the thing is that this theorem is something that is obvious, you have grown up with these things, but there is a formal way in which one has to do these things in order to ensure that there is no circularity of reasoning, in order to ensure that you are not mixing up the language and the meta language, to make clear where your reasoning is. Is your reasoning is at the meta language level or is at the language level? To make all those things clear, let us look at this proof. I hope you are all able to see it, but if you are not able to see it, so what I am going to do is I am going to use a standard proof by contradiction. So, firstly, this is an if and only if characterization, which means that there are proofs. There are two parts to it. The hypothesis logically implies the conclusion and the conclusion logically implies the hypothesis. So, there are actually two aspects to it. So, those two aspects are delimited by these arrows, which I will define. These are, so there is one part of the proof in which I take the hypothesis, I assume the negation of the conclusion and I prove that there is a contradiction, right. The second part of the proof, I assume the conclusion and the negation of the hypothesis and prove that there is a contradiction, right. So, I am doing both. This is to establish how one would expect proofs dealing with the semantics of propositional logic to look like, right. Okay, firstly, and of course, as I said, part of this is the fact that we are using standard mathematical reasoning also in our proofs. Yeah. So, okay, so assume that this formula is not a tautology, that means there exists a truth assignment tau such that I take this entire formula and that gets the value 0 in the Boolean algebra, and this is possible by essentially properties of the Boolean algebra and from the semantics of the meaning function t of tau, that this is possible only if this holds, this, yeah. So, notice that our semantics was by structural induction. So, the natural thing to do is to go down the formula. The root operator of the formula is this arrow, is the conditional arrow. So, we replace that by and the conditional arrow exactly represents LEQ dot less than or equal to dot, and that is what this means. Yeah. So, this Boolean object, which should actually be which is brown in color, T of some green thing in under tau is something that comes in brown in color, right? Yeah, and similarly this is some brown object that should be equal to 0, which is possible only if this conjunction is 1 and this is 0, otherwise LEQ dot will not be 0, right? We know that from the properties of LEQ dot. So, we are looking at all the properties of the underlying Boolean algebra, the properties of the less than or equal to dot. Yeah. Okay. So that is why this is an if and only if, all this is if and only if, remember that. So, this works both ways. So, I can go from the top down or from the bottom up. Yeah. Okay. So, which means that this is possible only under the semantics of AND, which is a dot, and if that is equal to 1, if this conjunction is equal to 1, then every individual in this conjunction should also be equal to 1, right? And this, I am sorry, this right bracket should not be there. This tau of psi tau should be equal to 0, right? Okay. Now, this of course, this last statement directly contradicts the notion of logical consequence, because what we are saying is, so therefore, that the individuals are all true, but psi is false, and therefore, gamma cannot be a logical consequence of thing. But I did not, I should have actually initially said assume gamma is part of this hypothesis is that gamma is that psi is a logical consequence of gamma, and that gets contradicted here, right? Now, as far as the second part is concerned, so you assume that the conclusion is a tautology, and assume that the hypothesis is false, which means that psi is not a logical consequence of gamma, and you just apply the semantics. So, this implies that there must be a truth assignment tau such that this holds, where of course this right bracket should not be there, and this is the same as this, and I can work this backwards, which leads to the fact that this whole thing should be equal to 0, but we assume that this is a tautology. So, under all truth assignments, the truth of this will be equal to 1, and so there is a contradiction, and therefore this so we have therefore we have shown both ways, right? We have shown the if and only if. Now, this is a tedious proof, right? It is meant essentially to state that we are using existing mathematical principles ourselves to reason metalogically about the concepts of logic. So, we are essentially treating logic also as a branch of mathematics and using the same principles of reasoning. Right. So, we might actually prove several other results. So, one is, for example, that for which I am not going to give proofs. These proofs are too tedious. We will do more interesting proofs later. So, let gamma be a finite set of propositions and let psi be any proposition. By the way, this psi should be green in color. Then gamma, then psi is a logical consequence of gamma if and only if this whole thing is a contradiction, where I take all the assumptions. So, gamma is essentially like the set of assumptions, and psi is like a conclusion from those assumptions, and essentially we are saying that if you take all the assumptions and the negation of the conclusion, then what you should, and form a single formula, that has to be a contradiction. Yeah? If that is a contradiction, and this is the reason for this theorem is that many of our implementation mechanisms will actually rely on this, right? It's trivial but tedious to prove this theorem, but it can be proven in the same way by using the semantics of the individual formula. Yeah? So, I will not going to prove this theorem. right. So, a formula phi is a tautology if and only if not phi is a contradiction or not phi is unsatisfiable. So these are things that we will use later in our algorithms for proving, for proof basically. But the notion of proof itself is something that I will have to formally define. Okay, right. More importantly, let us come to some, so there is a notion of logical implication, and here is where it is important to distinguish between what I write and what most books use. Okay, so there is a notion of logical implication which essentially means that, and that is denoted phi implies psi. So this black implication sign is exactly the same, note that we used here, right. So I'll keep using this for all characterizations, yeah. This black implication, remember, is not part of the language of logic, is not part of, that is why it is black in color, right. All that we are saying is that this a logical implication is a metalogical concept, and logically it refers to the validity of a conditional statement in propositional logic. So you take the conditional statement phi arrow psi, if that is logically valid, or if that is a tautology in the case of propositional logic, then and only then can you say that phi logically implies psi, okay. Logical implication is, so our notion of logical implication, of course, so this conditional arrow, what is it? It is that less than or equal to dot, right. What is less than or equal to dot? Just less than or equal to dot essentially says phi logically implies psi if and only if phi is no more true than psi. The truth of phi is always less than or equal to the truth of psi. The less than or equal to dot also says that false is less than true. Okay, a false statement is less true than a true statement basically. So logical implication essentially says therefore that the truth of the left hand side of the implication is in some degree less than or equal to, is no more than the truth of the right hand side of the implication. Yeah. So you have to look at, so one of the major problems a lot of people have in dealing with sentential logic is this notion of material implication. The standard problem has always been that the material implication has always been defined as something with the truth table 0, 0, 1, 0, 1, 1, 1, 0, 0 and 1, 1, 1, right. You take any standard book, A arrow B is defined like this, and it's always a matter of confusion to the beginner what exactly is meant by this kind of a truth. When everything is false, how can you still have true? That's one thing, right? That is one problem. So the way to understand material implication, which I am calling logical implication, but it is called material implication, is to understand it as some kind of measure of the content of truth. And you are just saying that if a statement phi logically implies psi, then the truth content in phi is no more than the truth content in psi under all circumstances. Yeah? And all our mathematical theorems are stated essentially in that fashion. So in a certain sense, if you look at the hypothesis of a theorem and a conclusion, basically all that you are saying is that the truth content of the hypothesis is no more than the truth content of the conclusion. More, and in the case of if and only if characterization theorems, you are essentially saying that their truth content is exactly the same. So, two statements phi and psi are logically equivalent, not semantically equivalent necessarily, yeah. Logically equivalent means where the semantics is restricted to the notion of truth or falsehood. They are logically equivalent if and only if the biconditional is valid, okay. Most books on logic do not distinguish between the conditional and logical implication. Most books also do not distinguish between the biconditional and logical equivalence. But the biconditional is actually an operator within the language, and logical equivalence is a concept outside the language, right. And in our mathematics also, it is very common to replace one by the other. But then you have to understand in what context it is done, So any formalization may have to distinguish between the two, and that you have to keep. Unfortunately, our logicians are also careless with their notation. So most books will not distinguish between these two. The fact that logical implication is a validity of a conditional, where the conditional belongs to the object language, but validity itself is a logical concept. And similarly with the biconditional and logical equivalence, that distinction is usually not drawn in most books on logic, yeah. But I would like to draw that, because that's how we like to clearly keep the object language different from the meta language, yeah. Okay. Now what you are saying by this logical equivalence is that the truth content, if phi is logically equivalent to psi, then the truth content in phi is exactly the same as the truth content in psi, yeah. So what are you saying in particular, from the meaning of truth, what you are essentially saying is that you take any truth assignment to the atoms of propositional logic, phi and psi will be true at exactly the same points and will be false at exactly the same points, yeah, right. So we call this logical equivalence, and not just equivalence, though often it is just called equivalence, yeah.
So these single arrows within the language,
yeah, this
we talk of these for a given truth assignment, that it may or may not be true for a given truth assignment, but the double arrow is a tautology for all.
Yeah, is for all truth assignments. But what we are saying is this, you're talking of this logical implication?
But single arrow within that green, within the language.
Yeah, this single arrow is the conditional less than or equal to dot, right, operator, which essentially says the truth of phi is less than or equal to the truth of psi.
This depends on what particular truth assignment.
Yeah, whether this whole statement is true or not depends on a particular truth assignment. But this validity means that for all truth assignments, the truth content of phi is less than or equal to the truth content of psi. If it is so for all possible truth assignments, then phi logically implies psi, right? Remember that the number of truth assignments that you can make is uncountable, is uncountably infinite. There are an uncountably infinite number of truth assignments. In spite of that, okay, so which means that any kind of formalization will have to make it come into some kind of finitary domain and keep it at least at most countably infinite. Yeah. Yeah, so this is what, so this is part of the object language. This arrow is, single arrow is part of the object language. This double arrow is part of the meta language. It is a logical concept independent of truth assignments, right. So we are, In all these logical concepts, we are abstracting away from truth assignments, from individual truth assignments. That is what most of the logical concepts will do, because you have to abstract away from the individual truth assignments because of the fact that there are an uncountably large number of truth assignments, and we still want some symbolic way for dealing with objects of the language. Right? So initially, so you understand what the enterprise of mathematics and logic for the last 2000 years has always been characterized by how to give a finite characterization of some infinite object. So linguistically, it reduces to saying, is there a finite length sentence I can use to characterize some infinitary property? So it starts with basic sets, enumeration of sets, right? You take an enumeration of a set. If it's a finite set, of course, it can be enumerated in finite time. But if it's an infinite set, you can't enumerate it in finite time. So what do? You look for a property of the elements of the set which can express it by abstraction, right? This in standard school mathematics, it's called, I think there is this roster form and the set builder form. That set builder form is a definition by abstraction where you are trying to use a finitely expressible property to express properties that to express the collection of all objects which might be an infinite set, right? This has always been one of the problems in one of the things. You always try to do an abstraction so as to characterize some infinite property in some finitary fashion, and this is one. This is the first in this course. But if you just go through a flashback of all your mathematics, starting from, let's say, 5th standard or 6th standard, where where algebra came up for the first time, not arithmetic, algebra. The use of that variable x is a finitely expressible thing for possibly an infinite set of values. So various tools in mathematics essentially try to express the infinite in some finitary fashion. Yeah? Okay. So that is there throughout the history of mathematics actually. And so this is what logical equivalence is about. And now we come to essentially back to an algebra, because now this any programming language or any formal language is actually an algebra, right? So we can also think about these concepts as algebraic concepts. So you take, okay, so now phi logically implies psi if and only if essentially this holds, right? Remember from the previous theorems, you are saying that phi arrow psi should hold, and then from the first theorem on logical consequence, phi is like a singleton finite set gamma, and psi is a logical consequence of phi, and so this is essentially what it does. By the way, this set braces is something that we will give up if there is going to be only one. Even if there are going to be a finite number, we will simply write it as something like this, phi 1, phi n, psi, right? This is to indicate that it's a finite set, and psi is a logical consequence of a finite set. So these set braces will all be given up as part of the, it's no longer going to be part of the notation. But for the moment, since I said that gamma is a set, I put it, yeah. Okay, phi is logically equivalent to psi if and only if phi logically implies psi and psi logically implies phi. Remember, this and is black, It is a metalogical AND, right? It is not a logical AND. Okay. Logical implication is a pre-ordering relation on the set of propositions, right? So essentially I can think of this, so all I am saying is that I can think of this logical implication and logical equivalence as essentially subsets of P naught cross P naught. Yeah. So I can take a purely algebraic view and think of this as a relation on, so I can think of an algebraic system in which I actually have a carrier set P naught and I have these two relations. Yeah, this is an algebraic system. It has no operators, but it has two relations. It's like you take an algebraic system like the natural numbers under less than or equal to, right? So it's really an algebraic system. Natural numbers under, let's say, addition and multiplication and less than or equal to and so on. So it's really this set n which is the carrier. There are two operators, let's say plus and addition and multiplication, and then I might have these two relations. So this is an algebraic system, right? Right. So I can take propositional logic P naught under logical implication and equivalence as an algebraic system with no other operators. Yeah. So if I consider this system, okay, the other thing of course, and this is also easy to prove, so a relation also has its inverse, right? So in fact usually the inverse is represented by implied by. So one of the things we say is when phi is equivalent to psi, we say that phi implies psi and is implied by psi, right? So this of course is the inverse of this relation. Okay, so you take the kernel of this relation. So this is a pre-ordering relation on this set P naught. So logical implication is a pre-ordering relation, which means it's reflexive and transitive. And if I take the kernel of this pre-ordering relation, which means I take the intersection of this pre-ordering relation with its inverse, whatever common elements I get, that forms an equivalence relation. That's an equivalence relation in the algebraic sense. So all I am saying here is that logical equivalence is also an equivalence relation on P naught. So it's an equivalence relation, so it is reflexive, transitive and symmetric, right? So essentially if phi logically implies psi, then psi logically, if phi is logically equivalent to psi, then psi is also logically equivalent to phi. So it's an equivalence relation in the standard way in which we talk about relations on sets. And the set here is the set of propositional sentences defined over a collection, an infinite collection of atoms, right? So you have an algebraic system, but there is more to it. It's not just an equivalence relation, it is a congruence. Is everybody familiar with the notion of a congruence relation? If you want some analogy, go back to Euclidean geometry. Triangle congruence is a congruence relation on triangles on the plane, right? Similarity, triangle similarity is an equivalence relation, okay? They are both equivalence relations, both the congruence of triangles and the similarity of triangles are both equivalence relations, but there is a difference. Triangle congruence is actually a congruence relation on planar triangles, whereas similarity is not a congruence relation. Does anybody, can anybody tell me what the difference is? Does everybody know what an algebraic congruence is? It has to be preserved under all contexts. So if you were to take, so if I were to take take some polygon and divide it up into triangles. Yeah, right? Now this is like an algebraic, this is like a geometric figure. Now what we are saying is, if have you come across this Tangrams? This game called Tangrams? Tangrams, you have a set of plastic pieces, all planar. They are all basically various kinds of triangles, and you put them together in order to form some other geometrical figure. Convex or non-convex, it does not matter, right? So this is like 5 tangram pieces put together to form this pentagon, let's say, right? Now it's possible, now if I take a triangle similar to this middle one, but not congruent to it, okay, and if I remove this triangle and try to fit this in, I do not get the same figure. However, if I had another triangular piece congruent to this triangle, then I can replace one by the other. So that means that there is a context or a framework in which if you replace congruent objects by congruent objects, then the framework does not change. Whereas if you replace an object by only another object which is not congruent to it, but is, even though it might be similar, the result of the replacement does not give you the same structure again, right? So that structure preservation or context preservation is what distinguishes a congruence from an equivalence. And the interesting thing about logical equivalence is that it is a congruence relation on this set P0. So the standard algebraic method for proving the congruence of any relation is to actually look at it under various contexts, right? So all that we are saying is, so here the framework is provided by some arbitrary formula chi, let us say. So you take the operator, so as I said, propositional logic is also an algebraic system with operators like and the green and the green or and the not, the arrow and the biconditional, right? So you take any context made up of these, logically equivalent propositions can be replaced by logically equivalent propositions and up to logical equivalence. The truth value will not change, and that is what this says. And usually, so what it means is that if phi is logically equivalent to psi, then not phi is logically equivalent to not psi, and for every formula chi and each of these binary operators of the language, I can replace phi by psi in each context. So this star indicates you take any of these, any or all of these. It will happen that phi star chi or chi star phi is logically equivalent to psi star chi or chi star psi respectively, right? So this is how contexts are created, right? The interesting thing about any algebraic congruence is that we prove it only for these, but it holds for any complicated framework you might form out of these operators. So if I define a new operator for example, if I define a new operator called 0 dot, which is which I say I shouldn't use phi and psi, maybe I should use some theta and chi, let's say. If I define a new operator theta and chi, let's say as naught of theta and or of chi or theta, for example, I can define some new complicated operator. I can even go further than this, yeah. What we are saying therefore is that you take any of these operators, then if phi is equivalent to, if phi is logically equivalent to psi, then I can replace wherever phi occurs. So, for example, in this context, phi O dot chi is going to be logically equivalent to psi O dot chi, right? And for that, by structural induction, it suffices to prove just for each operator, right? This is true not just of this system, but of any algebraic system. So, if you have done any kind of elementary abstract algebra, congruence would have been defined like this, but what they actually mean is that for any complicated operator that you might define with the existing operators, in that context, the replacement of equals by equals does not change the value. Yeah? Okay. So, it is sufficient. The number of different such operators like this O dot that I have done here, given here, the number of such different operators is actually at least countably infinite. But all we are saying is that by structural induction it is possible to prove that for any such, if for any such operator that you might define, this will also, this fact will also hold, if you have proved this theorem for the individual operators in the language, right? Is that fine? So, it is actually a, so congruence is defined in most mathematics textbooks simply as being as the relation being preserved under each operator, but the effect of that is that it is preserved under any operator that you might define using the individual operators, right. So, it is sufficient to prove this case analysis